All right, welcome to another week. This is week 3. Um, and let's get started. So, announcements. So, since we didn't enable late submissions for homework 1, so students were not able to use their late slip days. We apologize for that. So if you do submit homework 1 late, we'll just count 1 slip day against you, and that's it. Okay. So it doesn't matter when you submit your homework 1, we'll just take 1 slip day from you. So please try to, if you haven't turned it in yet, please do so as soon as possible because the mini project 1 has been released. If you haven't submitted the homework mini project form for homework 1, please do. That will also be part of your grade. So the grade sheet is now up, so you can click this link to access your grade. Well, currently we haven't calculated grade yet, but you can see all of your attendances for your homeworks and discussions. You will also be able to see how many slip days you have and so forth. And if there's any issues with the grade sheet that you have, please create a private ed post so that we could figure out something, what's like the discrepancies. And to find where you are on the grade sheet, you simply mod your student ID number with 99,999. So Mini Project 1 Cal Finance has been released. It's due in around 2.5 weeks on Friday, March 7th. And there is a checkpoint 1 in there, but you don't need to submit anything. That's just to help you stay on track. So if you're able to meet this checkpoint by that day, you're on good progress. And we think that 2.5 weeks is more than enough to finish this project. So yeah. Attendance cutoff time again is 15 minutes after lecture discussion. And if you have any feedback, we do appreciate, again, any feedback you have in the attendance form. Questions about logistics for this week? Yes.
Where can we find the homework mini project form?
So the question was, where can we find the homework mini project form? That is in the Notion, if you scroll all the way down the submission. Yeah. Other questions? Cool. All right, so for today, we're going to really quickly recap Swift UI. Then we're going to talk about a really important feature of Swift, which is closures. Then we're going to talk about how we could have data and flow it into our Swift UI views. And then we're going to talk about different kind of views that we could use in Swift UI. For example, for each to iterate upon a list of data using lists, sections within lists. And then we're going to have an important conversation about view identity and what kind of circumstances or how does Swift UI differentiate two views. So just to recap from last lecture, the thing that you should really take note is that a view defines a piece of UI. So every view in Swift UI is UI, and every UI in Swift UI is a view. So these are just some of the Swift UI views. Again, they form the fundamental building blocks of how we build views and also our custom views in Swift UI. And you can think of them as Lego bricks. Each view has a particular characteristic, and we could basically put them together using view composition to create more complex kind of views that we want. So we use composition to create more complex views from other simpler views. Just to recap on stacks, an H stack is a container that contains horizontally or aligns its subviews horizontally. A V stack is a container that aligns its subviews vertically, and a Z stack aligns its subviews on the Z axis. So in the axis that is pointing away or towards your computer or towards you. And we talked about how we could use view modifiers to augment a view's behavior properties. For example, we could add foreground style to basically change the text, or in this case, the text foreground color. And we could use the bold view modifier to bold the text. And order matters. And the reason why is because the subsequent or the last view modifier that you have down here applies upon everything that you have above. So each view modifier essentially creates a new view entirely. So it's very important, especially when you have background colors and paddings, to make sure that the views or view modifiers themselves affect what you want previously. And SwiftUI is declarative. You basically tell it what you want, and SwiftUI basically will handle much of the heavy work for you. So I'm just going to quickly go over what we did last lecture with the demo. And we're just going to highlight some key important topics that I want you guys to take out of. So going to what we didn't leave off like this. I already filled up much of the UI for you. There's nothing after discussion two, it should be quite familiar of how this everything works, but I just want to point out some kind of key things. So for example, one of the view modifiers that we didn't touch upon is this frame. So frames, the frame view modifier, you can basically specify how big you want your view to be. So in this case, I want this whole basically Swift, this repo or this view right here to be only the height of 300 points. I can specify its width, but since I omitted the width, I'm basically telling SwiftUI, take up as much available horizontal space as you want. But I want the height to be of 300 points. So that's what it's doing right here. And then also with the overlay view modifier. So this overlay view modifier, you're able to, it's sort of like a Z-stack. You're able to overlay some other view on top of what you have currently. So right now with this overlay, I'm able to create this rounded border on these buttons themselves. So that is overlay. And on the repo stats here, again, I just kind of filled out the UI. It's pretty basic. Again, you got your images, text, HStacks, and HStacks. But as you notice here, we could see that this right here is for this 67.3K stars, this view right here. And the following HStack is the view corresponding for the 10.3K forks view right here. Now, what you notice is that these two views are what? They're really pretty much the same thing. And the only differentiating thing about these two H stacks is the arguments into the image system name, the text, and this other text. But everything else is the same. So does anyone have any idea how we could improve this code so that we can make it perhaps reusable? What should we do instead of here? Instead of having these two hard-coded H stacks. Any ideas? So what we could do is that we could basically refactor or basically take this H stack and make it as a separate struct, another view itself. And then we could reuse it and just pass in whatever data we want. So what I could do is down below here or in a separate file, I can create this new view called repo stat view. And again, this is another view. And here is basically the template that exactly what we had before. But instead of hard coding this image system name, the text, and this another text, I'm passing them as arguments into this view. And what that allows me to do is that if I go back up here, I could delete everything I have here. Ah, doesn't work. Sorry, give me 1 second. I could basically I could basically just use the view that I just created as a custom view and then just pass in the relevant arguments into it. And it will just show up just like before. Does that make sense? So again, whenever you see you're reusing a lot of the same code, you're copying and pasting, it's better to refactor it into its own custom view and then pass in the relevant information into there instead. Cool? Yes? Does this make sense? This is really important. So, yes? Okay, cool. Thank you. All right. So, going back to the slides now. So, as you notice, some of the symbols that I've used with system name, those are SF symbols. And those are built-in icons built into Apple's operating systems, crafted by Apple, that you could use right within your apps. And the reason for this is that you could provide a sense of consistent familiarity with the other icons that Apple use within their operating systems, and they're customizable. So you could set the font weight, you could change the color of them, and so much more. And to get those icons, you could download the macOS app via this link right here, and you could basically browse through the inventory to get whatever image you want or symbol you want. All right, so that was Swift UI. So next we're going to talk about a unique feature. I won't say it's a unique feature, but it is an important feature of Swift. And a lot of Apple's code or APIs, they heavily use closures. So what are they? So they're self-contained blocks of functionality that can be passed around and used within your code. So if you have taken 61A, they're basically lambdas. So they capture and store references to any constants and variables from the context in which they're defined. And we call this capturing and storing references as closing over those constants and variables. So there are three types of closures. One of them are global functions. They don't capture any value. They're just defined globally. And then we have nested functions, which is basically a function within a function. And the closures for that, they have a name and they also, sorry, they can capture values. And the last is closure expressions, which are unnamed closures written in a lightweight syntax that can capture values like nested functions. And the third type right here is basically Python lambdas. So let's kind of talk about what capturing means. Again, so capturing is retaining a reference to constants and variables from the surrounding context or environment, even when the original scope that defined them no longer exists. So for example, again, this might be a bit confusing, but once you take a look at it a bit more, it will make more sense. So here's a function called make incrementer, and we accept a parameter called amount, which is a type integer. And here, this is the return symbol. What are we returning out of this function? We're returning another function. So this returns a function that accepts no parameters, and that function's return type is of type integer. So within make incrementer, we have this variable called running total, which is initialized to 0. And then within here, we see a nested function. And that nested function is our type 2 in our previous slide. And that is a closure. That's a type of closure. And within the incrementer here, we can see that we are returning an integer. And within the function, we basically add the amount that was passed into make incrementer to the local variable running total, and then we're returning it within incrementer. And then again, what we're returning in make incrementer is the function incrementer. Okay, and this is like, have you watched the movie Inception? Yes, this is sort of like that, right? It's a dream within a dream, and you're trying to get out of the internal dream back to the outside dream. So this is basically Inception. So again, right, incrementer is a closure. It can capture it can get a reference to running total and amount, even if make incrementer goes away. Okay, so it has pointers to running total and amount. It can keep track of them. So let's see how we could use make incrementer. So I called make incrementer, and I passed in 10 into amount. And the type of what it's returning is a function. So increment by 10 is actually a function, and that function is incrementer right here. So when I call increment by 10, I'm actually calling incrementer. So when I do that, I'll get the value of 10 because I'm adding 10 that I passed into here, and I'm adding to the running total, and I'm returning that running total, which is now 10. If I call increment by 10 again, I'll get 20 because right now the incrementer has references to running total. Okay, so it keeps track of it internally, and now when I call it again, I'll just add the amount that passed in, which is 10, right? To running total. Running total is now 10, 10. So 10 plus 10 is 20. So I return that out and I keep on going. So if you create a new incrementer, so let's say you call make incrementer somewhere else again, it will have a separate running total instance. So if I call make incrementer again and I pass in 20 and I call that, increment by 20 and I call that, I should get 20 now. So if you create a new incrementer, they have separate references to the running total. Okay. So again, it's a bit confusing, I know, but let's take a look at an example of how we could use closures. That was more common. Usually you don't see nested functions, but this is what you see, the last one, the last type. So there's a method called sorted, and it is a closure in a very brief and focused syntax. So sorted accepts a closure that takes in two arguments of the same type of array contents, and it returns a Boolean for ordering. So if it returns true, that means the first value should appear before the second value, and if it's false, the second value should appear before the first value. So for example, if we have an array of strings and we call sorted on it, the closure type would be string returns bool. So we're basically passing two strings into this closure, and if it turns true, that means this first string should appear before the second string. If it returns false, then this string should appear before this first value. So let's take a look at a more concrete example. So here we have this list or array of names, and it's just strings. And we have a function here called backwards, which accepts S1, S2, which are strings, and returns a Boolean. And again, we want to sort this array backwards. So we return S1 is greater than X2. And what this does is that it compares these two strings in lexicographically order. So we're going to go from the first letter. Is that letter, for example, is A greater than B? No, so returns false. Okay, and then that's this function. And so what we could do is that we could, call sorted on names, and then sorted returns or accepts a closure. And we're basically passing backward into here. So what this does is that it's going to give us a new array that has all the elements satisfying this backwards function. So everything is going to be reversed or sorted so that let's see, Iwa is going to be, in the first element, and then Daniela and so forth. All right, so that was a backwards function. Now we could convert this regular function into closure using this syntax. So we're going to have our curly brackets, and then we're going to have our parentheses. Inside those parentheses is going to be parameters, our arrow for return type, and then this in keyword to separate this declaration from the actual function statement itself. So what that looks like in writing this closure syntax is this. So instead of passing backward the function into it, we could basically write a closure to pass it in line within the call site. So here we're basically saying, I want to sort names by this function. And this function accepts two parameters, S1, S2, both of which are strings. And this function returns Boolean. And this in keyword separates this function, the parameters and return type from the actual function body right here. So actually we could do better. So we could rewrite this like this. So, oops. So what we could do is that we could actually have everything in one single line. We don't need to have it in three lines. We could do better. And we could actually drop the data types of S1, S2. Why? Well, because arrays, they contain the same data type. So Swift is able to infer that, hey, S1, S2 has to be of type string. So we don't need to explicitly define that. And we could do better. So we could actually redrop this return keyword because it's implicit. And we have to return something here. So this is what's returning. Again, this is a Boolean right here. And we could do better. So we could simplify this into something like this. So this $0 and $1 are something called shorthand argument names. And they are basically referencing the parameters. So $0 is the first parameter of this closure or function, and $1 is the second parameter of this function. So again, it's inferred by expected function type. The $1 is the first argument that we're passing into here, and the $1 is the second one. So what we're doing here again is we have these names, and we're sorting each basically pair by this condition. Okay. Does this make sense a little bit? Again, it's a bit weird, but you'll see more in the mini project. Okay. Any questions? Okay, cool. All right. So next, let's talk about how we could pass data within our views or how we can populate them. So I have this view right here, and this view has this property called num taps, and it's initialized to 0. Again, within this body right here, this is what this view displays, and it displays a simple button. And what does the button have? It has an action, and if you know this is actually a closure. This is a closure right here. And when we tap on this button, we'll increment num taps by 1. And this right here is also a closure built within the SwiftUI API. You don't worry about too much about it, but this is actually closure that uses. And within this closure, we're passing in the actual view. This is a text. So as you can see, Apple's APIs, they're using a lot of closures here, even though it doesn't seem like it. So these are actually like functions right here. So, but when we do this, we'll get an error. And that error is left side of mutating operator isn't mutable. Self isn't mutable. Now, the problem here is that structs, remember, conform to value semantics. So that means that when we basically assign a new variable to a struct instance, it gets copied. Or when we pass in a struct instance into a function, it also gets copied. Now, the problem here is that within the struct, we can't mutate its own properties. And the reason for this is because the compiler or Swift itself doesn't know if the origin of the struct instance is declared as a var or a let. Remember we could declare variables as either var to make that variable mutable and let to declare that variable is immutable. Well, within the struct context, Swift doesn't know if that variable is var or let. So by default, structs are immutable. So we can't do this in this circumstance. So we have to do something else. So again, regular struct properties cannot be mutated within their own structs. So the question is, how do we mutate these properties? So SwiftUI provides something called @state. What that does is it declares a source of truth in a view. So to use @state, we basically prepend this variable with an @state property wrapper. So this, whenever you see an symbol, this is called a property wrapper because it wraps this property with some additional functionality. So what this does is that we're telling SwiftUI to allocate somewhere else in memory for this num taps. And what that means is that we're saying to SwiftUI, hey, I want you to take care of num taps for me. And whenever num taps changes, SwiftUI will announce it. So for example, when num taps becomes 1, SwiftUI will say, hey, num taps changed. And it tells the body to re-render itself to update the new value for wherever it's using num taps. And it's really efficient. So it only re-renders views that are using the @state variables. So it only re-renders the part of the views that only use num taps. Okay. And we call those dependencies. So let's take a look at an example here. So again, this is the code. This is the view. And the only change from the last slide is that within this text view, we use string interpolation to show the value of num taps. So what I'm gonna do is that I'm gonna click tap me. And what happens is that the place where SwiftUI handles num taps becomes now 1. And since we have dependency from num taps here to this variable num taps, right, this @state, SwiftUI knows to update this text. So now it shows 1. Okay. So let's do that again. Let's click this button again. And the value now changes to 2. And since within our view we're using num taps, it will re-render view to show the updated value. Again, this is really important, so make sure you understand. Any questions? Does that make sense? Okay. So the next property wrapper that we will use is called something an @binding. So here we have, again, a similar thing that we had prior. We have num taps here, but the main difference is that I've refactored the button into its own separate view called incrementable button. Again, it's exactly the same thing as the prior slide, but I just kind of put it itself into a new Lego block called incremental button. Now, as you can see here, we have these two at states, one in content view and one in incremental button. However, the main goal here is that we want to sync up incrementables buttons num taps to content views num taps. What do I mean by that? I want this num taps to be the same num taps as this. They're linked. They're the exact same thing. However, since incremental buttons num taps is in an at state, this num taps is in a separate location than this num taps. So they're two different num taps in different places in memory. Okay, so these two are not the same thing. So again, you can think of SwiftUI managing two different variables. One is in content view and the other is in incremental button. So they're two different things. So to fix this, we could change the at state property wrapper in incremental button to an at binding. And then here we're passing not just a regular num taps, but the binding of num taps. We're passing this as a binding into here. And what this does is that it creates a read and write relationship. So this num taps right here within incremental button refers to this num taps in content view. And within the incremental button, whenever I update this num taps, since it refers to this num taps, it's actually changing this guy right here. Okay, so they're linked. Does that make sense? So remember how I said that the at state declares a source of truth? That is the original location. That is the actual data where it's located. And then within here, I'm just passing like a reference. So this num taps refers to the one up in content view. And whenever I'm updating this num taps right here, I'm actually changing the source of truth up in content view. Does that make sense? Okay. So again, the changes necessary is that I need to pass a binding. Without this dollar sign, I'm just actually passing an integer. With this dollar sign prepended onto num taps, I'm passing this binding, this special data type, so that within the incremental button, I'm able to not only read from it, I can also write back to it. So we annotate the property in the child view with an at binding. So whenever you see an at binding, that should be a child view from your parent view. So with an incrementable button, we could read the value of num taps stored here, and we could write back to the value stored here. Questions? Does this make sense? Again, it's very important. If you don't understand this, you're not able to do your projects. Okay. So let's take a look at an example of using at state and at binding. So within the API or SwiftUI API that Apple provides, one of them is something called a text field. And one of its, I guess, initializations is that you could pass in a text as a placeholder, and you could pass in a binding so that you could get whatever the user typed into the text field. So here in the content view, we have this at state variable that is just initialized to empty string, which is called text. And then here we have this subview called header text field, which accepts an at binding, and it's a type string. And then we have this simple vstack that displays the header, and below it, the text field where the user can input text. So what we're doing here is that, again, whenever you see an at state, that is the original location. That is the source of truth. My text variable is stored in content view. And then when the user types in the text field down here, where is the data being changed? So when the user in the text field types something, where is that data, that string stored? Ideas? So again, when I'm typing here, where is that string of text being stored? Where is that? Where is that located? Yes.
It would be the text available at the content.
Correct. So yes, that would be the text variable right here with the at state. So when I type into the text field, what's being populated or changed is right here. Okay, why is that? Why is it possible that when I type into text field, it's changing this thing right here? What mechanism is allowing that? Yes.
It's a pointer to the text.
Yeah, you can think of a pointer, exactly. So because of this at binding, this references this text with this $sign text passed in here, right? So since it's a binding, it references this at state text right here. And then when we're actually passing that as a binding into the SwiftUI text field, so that when internally, again, internally in Apple's code, when the user types within the text, right, I'm actually modifying this right here. So it's kind of, again, it's a bit weird, but again, when I'm again, when this, okay, so this is the declaration of the text field in SwiftUI. And the second argument you can see is a type binding string. It's not a regular string, it's a binding. So that when the user types in text field, I'm able to get the value out of it. Because you can think of this text field as a subview, and header text field is its parent. So when the user types within this text field, I can get back its value. So the text field here has write permission to whatever location, I want to write to. Does that make sense? Okay. So what I want to get out of this is that what I'm doing here with content view and header text field with the text and binding, it's basically the same thing from the same relationship from header text field and this text field right here. So again, it's a bit weird, but hopefully that will kind of stick. Questions? All right. So the next section is how do we represent a list of data? So we have this view called a for each, and it computes views on demand from a collection of identified data. So right now, you might see some examples are all hard-coded like text, right? From the Swift repo, everything is hard-coded. But wouldn't it be nice if we could create views based on some data? So right here, we can see that we have a VStack of just text, 4 text views. But what if we have an array of strings? Wouldn't it be nice to create some view using those strings? And so that's what for each does. So for each, you could pass in, for example, this iterable, which is this array of strings into for each. Now I'll talk about what this ID argument is in a bit. And here, what does this look like to you? What did we learn in lecture today that you see this pattern right here? What is this? Yes.
Closure.
A closure. So exactly. So you can see Apple's API, or basically the code that provide us, they're closures. What's really cool is that a VStack is a closure. This VStack is like a function. And here, these curly brackets, this is a closure. This closure accepts no parameters, and this is the return type of this closure. Okay, so it's very weird. They're using a lot of interesting, you know, abilities to do this. But yeah, I could think VStacks, HStacks, ZStacks are all closures. Yeah. So again, here in this for each, we're iterating upon each student, and we're getting that value back as this name here. So this function right here, again, this closure, it accepts a name, this parameter, and then within here, returning the view that we want to represent for each student, which is this text right here. Oops, sorry. So we're getting each name here, and then we're basically so okay. Internally, what for each is doing is that it's taking this function, right? And then it's passing Oski into name, Peter into name, Gunrock into name, and then it's displaying this text. Does that make sense? So again, internally, what for each is doing, it's getting this function, this closure. Okay, I have this closure. It accepts a name, right? So I'm passing Oski into it, Peter into it, Gunrock into it, Sammy into it. And what am I displaying? This text. So that's how it's using this closure, which is really cool. Now, each element within here, within this iterable, this array, must be of type, or must be an identifiable. If not, we provide a key path. And I'll explain what that is in a minute. So to make something identifiable, we conform to the identifiable protocol. If you have taken 61B, a protocol is an interface. It just basically has a list of requirements. So one of the requirements for a data type to be identifiable is this ID property. So you need to set it to some unique value. In this case, I'm using the UUID data type, and that's just an object to universally identify unique values in objects that's built into within Swift. So now what I've done is I successfully conformed the student data type or the struct to identifiable. So how do we work with structs or how do we work with data types that are identifiable? So within here, I've created a list of students and I just pass in students directly into the for each. So for each identifies each element because it's identifiable since each student has a unique ID. And it's using the ID property to identify each student. Now, if you don't want to use identifiable, you have to supply a key path. So now I remove the conformation, conforming to identifiable, and now I'm adding this new parameter called ID, or I'm passing this slash dot student ID key path into the ID parameter. And what this does is that it's basically saying, okay, for each, I want you to identify each student by its student ID property. That is what it's saying. So a key path is like a property. So does that make sense? So this slash dot student ID is basically referring to the student ID's properties of each student. And we're saying, hey, for each, I want to use that property to identify each student. So there's also a special ID called slash dot self. How many of you guys have taken 61B? Okay, good chunk of you. So you know what it means for a value to be hashable. So for values that are hashable, you can supply the slash dot self for the ID as an argument. And what slash dot self means, it means the whole object. So what Swift does is that it takes that object, right, that student, and it gives it into something called a hash function. So there's a special function that whatever value it takes in, it recomputes it into some other value, some other like number or whatever, and uses that as an identifier. Again, don't worry if this doesn't make sense, but just know that some supported values are hashable by default, and you could use the ID slash dot self instead. And you could also make your own data types conform to hashable. So again, hashing is introduced in 61B, so don't worry if this doesn't make sense, but just know that for some data types, it is possible to use slash dot self. So for example, strings are hashable. So we could ask Swift to compute the string's hash value, which is unique for every single string, and use it as an identifier. So SwiftUI, this for each, will use the hash value of each one of these strings to identify itself in relationship to the corresponding view. So that was for each. Now we have another built-in view that SwiftUI provides, and that's the list, which simply displays a list of items. It's a container that represents or presents rows of data arranged in a single column, optionally providing the ability to select one or more members. So here, how do we use list? It's very simple. Again, it looks like for each. You do a list, pass in whatever iterable collection of data that you want, and you get it back, or you provide the corresponding view for each element using closure like this. And again, the main difference of this for each is that a for each is static. So for each views that you have, it's not scrollable. But with a list, it takes that to a different level and makes your collection scrollable with this kind of default style. You could also create multi-dimensional lists with sections. So for example, here we have a section and we can specify a header to that section. it will just show up right here. That's the head, the section header. And then we can group again, we can group a view within a list using a section. So this for each is this right here, and this second for each is this right here. Okay, pretty simple. And so this looks very similar to the settings app in iOS, right? So this is how Apple uses. They use a list and sections. Any questions there? Okay, cool. Let's talk about view identity now. So my question to you is, are these two circles the same circle, or is it they're different circles, right? There's no answer to this because it could be both. It could be both. It could be the same. It could be different. I don't know. And that's a question of view identity. So when they are the same views, we call them they have the same identity. So if the views are the same, we expect the red to move to the blue, right? So we expect this red to move to the blue continuously as while it's going to be changing its color to blue. So same views, same identities. Now, if they're different views, that means they have different identities. So now, instead of continuously moving down to the bottom of the screen, we should expect the red circle to fade out and the blue to fade in because they're separate views. So there are two types of view identities. One of them is called explicit, and they're used by defining a custom or data-driven ID. So for example, within our for each, we saw this ID parameter. And what we're able to do is that we're able to associate each of the elements within this rescue dogs array to its corresponding view that we provide here. So an ID, the ID parameter is a form of explicit identity because we're saying explicitly, hey, SwiftUI, identify each element in rescue dogs to your respective or corresponding profile view. So if the data changes, SwiftUI is able to generate the appropriate animations automatically. So we're talking about deletions, insertions, and modifications. And so that's the reason why SwiftUI needs identifiable or using this explicitly using this ID is because for automatic animations, it needs to appropriately identify that data to its corresponding view. So this is what it looks like. So now when you, for example, select items, it's able to animate within the list automatically without having you to write any additional code. So if this data changes or updates, you're able to get automatic behavior, automatic animations from a SwiftUI. So again, when I delete something, when Rescue Dogs changes, SwiftUI knows how to animate it because everything is explicitly ID'd. So I know, hey, move this view down here or delete this, make it, change the view height, something like that. So SwiftUI handles everything automatically for you, which is really good. This second type is structural identity. So instead of explicitly identifying each view with an ID, we define it by its position in the view hierarchy. So here we have in the body, we can actually have conditional statements. We can say if let user equals user, and then if that is not nil, so again, this user right here, pretend that is an optional. So what we're doing is that we're saying, hey, is this nil? Is this, is there a value here? If there is a value, we unwrap it, we assign it to this new local variable called user again, and we could use it within here. Else, if user is nil, I want you to show this authentication view instead. Does that make sense? So depending on this condition, I could show logged in view if there is a user, or if there is no user, I'll show authentication view instead. So SwiftUI is able to identify each view based on the if statement, based on the branch of the if statement, instead of having to explicitly ID that logged in view with some, explicit ID or authentication with another explicit ID. I can just basically, SwiftUI is able to know, where it is located based on this conditional statement. So SwiftUI treats login view and authentication view as two separate different views because they're on two separate branches of this conditional statement. They're not the same. So illustrating this idea, we have this at state variable, which is show red, and it's set to true. Again, we have this conditional statement here. So if show red is true, we show this circle, whose color we filled it with red. If it's not, if show red is false, we show this circle with the color blue. Sorry, that is a typo. That should be colored dot blue or dot blue. So yeah, but you get the point. So if I mutate show red's value to be false now, it should transition to the blue circle by fading in and out. The reason for this is because they're separate views. They're not the same. So the transition behavior is different. So we expect the red one to fade out and the blue circle to fade in. Okay. Now let's take a look at the same example, but now with instead of having two separate different identities, two separate views, we're going to have just a single view. And instead of, having two separate views, we're just basically conditionally change the fill color of the circle. So this syntax right here with this $sign and colon, that is what we call a ternary operator. So this is a really condensed if-else statement. So what we're saying here is that if show red value is true, we show the color red. If it's false, we show the color blue. Okay. So when I change it to be false, the transition, there's no fading in and out because they're the same view. We're preserving the view itself and just changing its color. Does that make sense? So SwiftUI is treating this as just a single view, and we're just changing one of its properties. Make sense? Okay. So that is, again, the difference between explicit identity and structural identity. So the question that we're trying to ask is, okay, these two views with on our screen, are there in two different screen states? Are those views the same view or different? If they are the same views, then we call them this, they have the same identities. So SwiftUI applies new state to that view. So if they're different views, then they have different identities. So SwiftUI will appropriately transition them independently. So views are being created and being destroyed. So for example, in the if statement that we had before, right here, when show red is false, we destroy, or we basically rerun the whole body. This becomes gone, right? This becomes destroyed, and this becomes created, right? But here, with the single circle, nothing gets destroyed. It just gets, the same circle still remains, but we're just changing one of its properties. So again, there's two types of identities. There's explicit, which are defined by using custom or data-driven identifiers, for example, the ID parameter of the for each, and implicit, which are defined by the view type and position in the view hierarchy. And the reason for these identities is for SwiftUI to have the appropriate transitions and animations. So when it comes to structural identity, which one do you use? Do you use this one, right, with the conditional, or do you use the one with the ternary operator with just a single view? So Apple recommends you to prefer using the second approach, highlighted in red, so that it doesn't need to destroy the previous view and create the new view. So it's more performant. And usually the behavior that you want is usually the one showing here, right? Sometimes you want it to transition in and out sometimes, but most of the cases you just want to change a property of that view and not having it to have that default transition thing. So to use this second approach, you specify conditions within the view modifiers to preserve view identity using most likely ternary operators like this. Again, it's more performant since SwiftUI doesn't need to destroy and recreate views. Alrighty, so that comes to our summary here. We talked about closures. They're basically self-contained blocks of functionality that can be passed around and used within your code. They can capture variables from its surrounding context. And we could use closures with built-in Swift functions like map, filter, sort, and etc. We talked about the difference between at state and at binding. And at state declares a source of truth. And at binding creates a two-way read and write connection from a source of truth in a parent to a child view. We talked about a for each, which allows us to create static data from a collection of data. We talked about lists, which basically display displays a list of data, which supports editing and selection. We can group together similar data with sections. And then we talked about view identity. There's explicit and implicit. Explicit are like we define them using custom or data-driven identifiers, and implicit using the view type and position of where they are, like the conditional if statement that we've seen. And implicit and explicit, they have different behaviors when it comes to transitions, animation.